Hey everyone, welcome to the Explainer. Today we are going to act like math detectives and build our very own ultimate exponent rulebook, completely from scratch. We're looking at a super fundamental algebra concept, and honestly, rather than just memorizing a bunch of formulas from a textbook, we're going to figure out exactly why they work. Here's our roadmap for today. First, we'll build the exponent rulebook. Then we'll start multiplying and dividing monomials, dodge a really dangerous mathematical trap, do a couple of quick concept checks, and finally, we'll talk about transferring your new skills.
All right, let's jump right into Section 1, Building the Exponent Rulebook.
Relying on just rote memorization can totally fail you when you're stressed out on a test. But understanding the core mechanics, that stays with you forever. So we're going to use expansion as our proof. Take the product rule, for example. If you have x squared times x cubed, and you expand that all out, you've got two x's multiplying together and then three more x's. If you just count them all up, you have exactly 5 x's multiplying together, right? So the result is x to the 5th power. The rule simply becomes, when multiplying the same bases, just add the exponents. But the cool thing is, you never actually have to guess. You can always just write it out to prove it to yourself.
Okay, so what about division? Well, we can illustrate the quotient rule just through simple cancellation. If we have x to the 5th divided by x squared, expanding that gives us 5 x's on top and 2 on the bottom. Just cancel out the matching pairs, and boom, we are left with 3 x's on the top, which is x to the 3rd. This shows us that when you divide like bases, you subtract the exponents. But we do have to read the fine print here. This only works under the strict condition that x does not equal 0, because as we know, you simply cannot divide by 0.
Moving on, how does this logic build our third law, the power of a power rule? Basically, what happens when an exponent is raised to another exponent? Let's say we have x squared, and that whole thing is raised to the 3rd power. By expanding it out, we see it's just x squared times x squared times x squared. Break that down even further, and you can physically count exactly 6 x's multiplying together. This reveals a massive shortcut. We are really just multiplying the exponents. 2 times 3 gives us 6. Simple as that.
Now here's where things can look a bit intimidating at first glance. 0 and negative exponents. But don't worry, they make perfect sense. Any non-zero base raised to the 0 power is just exactly 1. And a negative exponent, it does not make a number negative, it literally just means division. It tells you to move the base to the denominator of a fraction. For example, 3 squared times 3 to the negative 5th gives us 3 to the negative 3rd. If we apply our rule, that becomes 1 over 3 to the 3rd power, which evaluates perfectly to 1 over 27. And again, this requires our base to be non-zero.
So, putting all of that together, we have our completed exponent rulebook. This consolidates all 5 of those derived rules into one incredibly powerful cheat sheet. Take a mental snapshot of this. We've got the product, quotient, power, 0, and negative exponent rules, complete with the formulas and those all-important conditions. This is the exact foundation we'll be using for the rest of the explainer.
Section 2, Multiplying and Dividing Monomials.
Let's actually use this brand new rulebook on some more complex expressions that have both coefficients, the regular numbers out front, and variables. When we multiply monomials, it's best to break the problem into 3 distinct steps. First, we group the similar parts together. So we take the coefficients 2 and 3 and group them. Then we group the x variables and then the y variables. Second step, we apply our exponent rules, in this case, the product rule. Multiply the numbers to get 6, add the x exponents to get 5, and the y exponents to get 3. And for the third step, always remember your fallback strategy. If you ever second-guess the rule, just expand a small part of it to verify your work. It's a very similar process for division. We divide the coefficients first. 8 divided by 2 gives us 4. Next, we apply our quotient rule to our grouped variables. For the x variables, 4 minus 2 leaves us with x squared. And for the y variables, 3 minus that invisible 1 leaves us with y squared. And just like before, double-check your logic by expanding out those repeated factors. Cancellation is absolutely your best friend when you need to verify a quotient.
Section 3, The Big Misconception Trap.
Okay, I need your complete attention for a second because we really need to navigate around a dangerous mathematical trap that catches so many students. Listen to this. Exponents are not added when terms are merely added. The trap is thinking that exponents behave the same way in addition as they do in multiplication. They don't. If you have an x squared plus another x squared, that just gives you 2 of those things. It's 2x squared. The exponent stays the exact same. Exponents only change when terms are multiplied, which is how x squared times x squared becomes x to the 4th. All right, moving to Section 4, Concept Checks and Recap. Let's see how well you've mastered the rulebook so far. Try solving this first one entirely in your head. What is the simplified result of multiplying 4a cubed b by 5ab squared? Remember those 3 steps we talked about. Group the coefficients, group the similar variables, and then apply the product rule. I'll give you a second to compute it.
Did you get it? The answer is 20a to the 4th, b to the 3rd. If you got that, you are absolutely correct. You expertly grouped the 4 and 5 to get 20, and you combined the variable exponents. Remember that single a and single b have an invisible exponent of 1. So 3 plus 1 gave us a to the 4th, and 1 plus 2 gave us b to the 3rd.
Let's do one more check, this time involving division. Simplify 15m cubed n squared divided by 3m cubed n. Keep a really close eye on what happens to the variable m when you apply the quotient rule here. And keep your non-zero exponent conditions in mind.
So the crucial takeaway here is exactly how that m variable behaves. 15 divided by 3 is obviously 5, but m to the 3rd divided by m to the 3rd is m to the 0 power. And based on our new rulebook, anything to the 0 power equals 1, so it effectively cancels out entirely. Then for n, 2 minus 1 is 1, leaving us with simply 5n.
Let's do a super quick recap. We've learned that expanding factors is the ultimate proof of our rules, completely beating rote memorization. We know we always need to state non-zero conditions for zero and negative exponents. We discovered that grouping is the secret to handling monomial multiplication and division. We cemented the awesome habit of verifying our answers by expanding. And maybe most importantly, we successfully dodged the big misconception trap. We will never add exponents when we are merely adding terms.
Finally, Section 5, Transferring Your Skills.
Before we wrap up this explainer, I want to take these skills out of the abstract math world and see how they apply to something real. I'll leave you with this provocative thought to ponder. If a bacterial culture's growth is modeled by a positive exponent, how do these abstract rules of negative exponents actually change the physical meaning of that model? Does it flip from growth to decay because we're suddenly dealing with fractions? Think about it. Keep exploring, keep questioning, and use these fundamental rules to unlock the math all around you. Thanks for joining.